Hello and welcome to yaymath.org. My name is Robert Adu and this project is called Yaymath in Studio. I love this little studio space with the hands holding all the other hands. I mean, that's essentially the reason I'm doing this work, so that what I do and I guess you could call it my gift or my offering, can reach out to you so that you can reach whatever gift it is that you're looking for. All right, this is all freely available on YouTube and it always will be. So with that, let's talk about solving nonlinear systems. I see it in my head, I know what to do, and now I'm going to offer it to you so that you can see exactly what I see. So this is what we mean by a system. It's two or more equations, all right? So if you have two or more equations, the question is, where do they intersect? Where do they line up? In linear systems, you have like two lines, let's say crossing here, and this would be the point of intersection, right, where they touch. Or they could be parallel and never touch, or they could be overlapping and touch at infinite points, right? So you could sort of, chop your way or do a 1980s, breakdancing situation with two lines of where they cross, okay? And usually you're gonna get one point of intersection or no points or infinite points when they overlap. What about when the systems are not lines, as we are about to do now? What if you had, let's say, a circle and a line? Right? If you had a circle and a line, what are the ways that they can engage? Let's get some visualization. You could go like this, and you could say no smoking. You can do that. Or Ghostbusters, so that would be 2 points of intersection. Or you could have maybe like no points of intersection. That could be no solution to this system. Or you could even like graze it over here and nick it. Yeah, better, boom. You can like have 1 point of intersection. So there's lots of different ways. These are the three ways in which a line and a circle can engage. So it's important to get that visualization before we get solutions. We can get two solutions or none or one. So let's offer an example. Let's do the circle x squared plus y squared equals 25. And let's do the line y equals, how about that one? 4 over 3x. Yeah, that should work. So let's get a visual. This would be, all right, let's take off this little hieroglyphical thing and use the real estate. All right, so here we have this graph. We'll start with the circle in blue. There's some blue right here. So we have the center at 0, 0, and we have a radius of 5, the square root of 25. So we go up, down, left, right, 5 from here. 1, 2, 3, 4, 5. A 1, 2, 3, 4, 5. A 1, 2, 3, 4, 5. And it's more fun to say a 1, 2, 3, 4, 5. Here we go. Now some people like to jump straight into algebra. Look, I'm not knocking that. I think it's really helpful to get a visual sense of what we're working with, okay? Now let's graph this guy in red. Here we go. So slope, intercept. The y-intercept here is plus 0, so we see the y-intercept is 0. And we have a slope of up 4, right 3. Here we go. A 1, 2, 3, 4, positive. A 1, 2, 3. Oh, there it is. And down. A 1, 2, 3, 4, and a 1, 2. Work with me. And you're going through. And as we did in our first scenario, we have 2 points of intersection. They are, I'll get the green one here. Yeah, green kid coming for the party. This and this. Technically, if you know your graphs, this problem is already solved. If you did this, let's say with graph paper, a little more exact than what I did, you'd get the two solutions. You just list these 2 points and we're done. But we're going to be thorough and we're going to solve it algebraically. All right. So in solving systems, one of the main methods is called the substitution method. The issue is we have two variables here, we have two variables here, but can we team them up to create an equation with one variable? Substitution method, this variable is already isolated, that's great. So I'm going to bring this y equals 4 over 3x in here. Observe, x squared plus squared equals 25. So this used to be y, and technically it still is, because instead of y, we're going to write, let's see if I can do this elegantly. Instead of y, there we go, it's going right in there. We're writing 4 over 3x. Is it true that y equals 4 over 3x? Yes, it's true. So in place of y, we're writing 4 over 3x. And now you'll notice we have an equation with only x involved, which is solvable. Proceed! X squared plus 4 over 3 squared is 16 over 9 x squared equals 25. We need to add fractions, so we require a common denominator. That denominator will be 9. Here it comes, 9 and 9. All right, continue to add. 9x squared plus 16x squared, that's 25 over 9x squared equals 25. Multiply both sides by the reciprocal, times 9 over 25, times 9 over 25. Notice I'm using levels so that I'm prompted to know how to cancel, all right? I would use this level here, right? Rather than go writing 9 over 25, it may not be clear what to do with these 25s, but if you use levels, some students like to do that, you'll know that the 25s should cancel. It pops out. Take that off. All right, all those go. 9 over 9 goes, 25 25s. So we get x squared equals none other than just 9. Take the square root of both sides. X equals 3 or negative 3. What number times itself is 9? 3. Or negative 3 times itself is also 9. And what do you think these points represent? Oh, baby. What is it, x or y? X. 3 over here. Negative 3 over here. Kind of cool. So those are the two x values of the points of intersection. Going to y. Which should we plug it in? The good news is it won't matter. It works for both. So let's pick that one. Let's do that one. So then that would be 3 or negative 3 squared plus y squared equals 25. It's kind of cool. So no matter what, we'll get 9 plus y squared equals 25. So this is the idea. We know that there's going to be two y values. So it was kind of cool to plug it in here because we're about to get both of them. Or we could have plugged it in here, but we'd have to do it twice. We'd have to plug in the positive 3 and get our y value. And then we'd plug in the negative 3 and get our y value. Either way, you're going to get two y values because visually we understand there are 2 points of intersection. So it's really powerful to have this sketch on the side. Okay, subtract 9 on both sides. And we get 16, square root both sides, y equals 4 or negative 4. And lo and behold, there they are, 4, negative 4. A luxury in the study of mathematics, not afforded to many other courses of study, is that we can check our answers within the problem. So imagine you're taking a test and you'll know whether you get the problem right. That's a huge luxury and fascinating to me, that you could actually know if you get the answer right by plugging it in. And we could do a quick spot check. Is 3 squared plus 4 squared equal to 25? 9 plus 16, 25? Yes. And we could do a spot check over here. So this would be 4 for y. Bring it down. This is like 4 equals 4 over 3 times, what? 3. That would work. Times 3 for x. Yes, it's true. These go and 4 equals 4, so we're good on that regard. All right, so it's an incredible luxury and really fascinating that you could check your own work. Let's try another. Okay, with these, we notice two different types of graphs as well, nonlinear. This one, we see only one of the variables is squared, so that's a parabola. This parabola is facing down. Y equals negative x squared faces down. And this happens to be a line. So again, we can get a visual fix. Let's do it over here. Parabola facing down, line. Do they never touch? That's possible. That's also possible. We have parabola, line here. Imagine they touch. They could have 1 point of intersection. Parabola, line. They could have 2 points of intersection. So have that sort of understanding going in so that you're not surprised when you see stuff. I would like to get a visual fix. Here we go. Y equals negative x squared faces down. This is a vertical shift of 4. So we go up 4. 1, 2, 3, 4. Starting there. And let's graph the sky in blue. This is blue. And it's facing down, you know, like that. So notice I'm not being super exact. You can be, but it's not completely necessary. if we're going to solve algebraically. And let's go 2x plus 1. We'll do that in red. Here, y-intercept is positive 1, slope 1, 2 over 1. Ah, looks like 1 right there. And then we got down 2 over 1. And we'll sort of, that's kind of cool. We'll make this one a mystery. But it does look like we have 2 points of intersection yet again. Let's find out how to do it. Substitution method. Here it comes. Instead of y, shall we write 2x plus 1? Sure, says Robert to himself. So here we have, I'll tell you what, I'll write it again. Negative x squared plus 4. And now this y in red is now going to be taken out. And in its place, I'm going to put 2x plus 1 for clarity. All right, equals negative x squared plus 4. All right, solve algebraically. Here we go. I'm going to bring everything to the left. Plus x squared over here. Minus 4, minus 4. Gown. This is x squared plus 2x minus 3 equals 0. All right, this is factoring time, or in French, le factor. Over here. I don't know if it's masculine or feminine. Actually, I think I looked it up. It's like a factorizad. Oh, I gotta look it up. I'm gonna look it up. A factorizad, a factorimor. It's not love. It is. Here we go. All right, two numbers that multiply to negative 3. I Googled it. Yeah, I'm that guy that Googles factoring in French. Multiplies to negative 3 and adds to positive 2. That would be plus 3, negative 1. That's right. Those two numbers multiply to negative 3 and add to negative 2. Solve for x. X equals negative 3. X equals 1. And we're not surprised by those numbers because we're going to put them in. Where would negative 3 be? Right here. Where would 1 be? Right here. Lovely. All right, and let's get our y values. Let's plug it in here this time. Y equals 2 times this plus 1. Y equals 2 times that plus 1. Here we go, plugging it in. Negative 3 and 1. 2 times negative 3 is negative 6 plus 1, negative 5. There it is. I was plugging in negative 3. 2 times 1 is 3, plus 1 is, no, 2 times 1 is 2, plus 1 is 3. There you go. Okay, solutions. Ta-da, that's all it is. Okay, so now we have two different graphs. This we know x squared plus y squared is a circle. Here we have y squared minus x squared is an ellipse because of this minus between the y squared and x squared rips it apart. We have this ellipse. It's going to go something like this and like this. Okay? So you know what? Now that we graphed two of them before, we don't necessarily need to graph every time. It's just good to get that habit, okay? Let's see if we can solve this without necessarily having to graph. At least maybe just having a feel for it. You know, you have circle. We could have 1, 2, 3, 4 solutions. It's kind of cool. Looks like a tennis ball in flight. There are 4 solutions here. 1, 2, 3, 4. We could have that. Or we could have 2 solutions if it just touches here on the edges. That would be kind of cool. Or we could have none. That always can happen as well. See that when they never touch. No points of intersection. Let's see which one this is. The second method for solving systems, besides the substitution method, is called the elimination method, when you add down. All right? If we add down these two equations, you will notice x squared and minus x squared, they cancel. They go. Bang, bang. Y squared plus y squared is 2y squared. And we have the equals. Bring it down. That's 60 plus 12, that's 72. And then divide both sides by 2, y squared equals 36. And then square root both sides, and we get y equals plus or minus 6. Okay, so we have potentially 2 y value answers. Let's put them here so far, 6 or negative 6. Now let's see if we can plug in. Tell you what, let's plug into the first one, see what happens. let's get x squared plus squared equals 45. And we could plug in 6 or negative 6 here. 6 or negative 6. It won't matter in a sense because we're squaring it. And we'll get x squared plus 36 equals 45. Subtract 36 both sides. X squared equals, interesting, 9 square root x equals plus or minus 3. Wow. So where do they go, right? You know, that's kind of interesting. With the knowledge that this could be tennis ball situation, we could have 4 points of intersection. And if you think of it logically, how many ways can you arrange a positive and a negative and another positive and a negative? Because even if I try to put I could put the 3's here, right? That would be both situations of 6 and negative 6, but I have not accounted for the negative 3's for x. So it turns out that this is going to be 4 as well. So here we can even separate them. Here you have your y is 6 or negative 6. I can do that again, 6 or negative 6. Here we had x at positive 3, and now we account for x at negative 3 as well. So that's every situation, every arrangement to arrange positive and negative x and y values. It's kind of interesting. You know, there's 4 points that work for both. Again, quick spot check. No matter what numbers you plug in, the 3's and the 6's, into these, both of them, it will work. It will work. It's kind of amazing, isn't it? You know, let's try the negatives here. That would be 6 or negative 6 squared minus negative 3 squared, no matter how you do it, equals 27. Make a little room for that. It works. 36 minus 9 equals 27. It's true. So no matter what negatives or positives you plugged into x and y, you would see that the equation verifies. It's awesome. Okay, one more. One more. Okay, for this one more, we notice inequalities. This is why we've been graphing this whole time, because the solution to inequality graphs are non-numerical. They are graphical. In other words, the solution for an inequality system is the graph itself with shading, right? Will the real slim shading please stand up for nonlinear systems? I'm about to show it to you. Here we go. Wow. All right, so let's do this. Gonna graph the first one. This is a Cirque du Soleil, circle. Radius at 4. 1, 2, 3, 4, 1, 2, 3, 4. Center at 0, 0. No shifting. 1, 2, 3, 4. 1, 2, 3, 4. Graph this guy in blue. There it is. Around we go. There it is. And then we have this. Notice x squared and y squared are both being squared, the x's and y's. The minus between. This is an ellipse. Whop, rips it apart. X is first, so it's the dominant force. So it's a lefty-righty hyperbola, not uppy-downy. If y squared were first, it would be up and down. So you'll notice that if we divided both sides by 9, which is standard practice for hyperbola, we'd get x squared minus y squared over 9 greater than 1. So this center is also at 0, 0 because there's no shifting inside. And we go left 3, right 3, left and right 3, up and down 3. So it's like there and there, right? The box is included with the y because that's this part of this box over here, right? That's the way to graph the hyperbola. But just for sketch's sake, we know that this is a left and right hyperbola because x is first. Okay, if you want more information on how to graph this specifically, check out the hyperbola video. Okay, but just in a crash course method, the x is first. It's a hyperbola going left and right. So there, there, and there, and there. All right, there's our tennis ball again. All right, so let's talk about where the shading is. You'll notice x and y squared both have to be less than or equal to 16. So values like that would be maybe like 1 and 1, for example. 1, 1 or 1, 2 or 0, 0. All those points that are included is everything inside the circle, less than the 16, really like less than the 4, right? So we're going to eventually shade inside this blue circle because it's less than. Over here, greater than 1, we need large values to be greater than 1 over here. Or even over here, we need large values. All right, points like 10, 0 would work here. 10, 0 is like way out here. So that means we're shading inside the hyperbola, right? So to be greater than, we're shading like to the extremes over here for this hyperbola. To be less than, for the circle, we're shading inside. So it begs the question, where is the only area, or the only region that's within the circle, smaller than the circle, but beyond or outside the hyperbola? And here it is. Make our little planet green right there. It's the only area that's within the circle but beyond the hyperbola. So this green region is the solution to this system. Nothing more. You don't write down points or anything like that. You depict it graphically, visually. Okay. Thank you so much for watching. I hope that helps solving nonlinear systems. I'm going to sign off in a nonlinear way. Baby. Baby. Nonlinear.